So let's do y equals 4 minus x squared, right? So that particular function. And let's find the min distance from the point 0, 2. So you can probably tell here there's two min distances, right? There's some symmetry here. So, but I just want to find the one in quadrant 1, right? So our question is, find the point on y equals 4 minus x that has a min distance from the first quadrant to 0, 2. Right? So we know what's going on here. Yes? I typically put a min distance problem on this test. I probably will put a geometry problem on the test as well, right? So remind me to kind of write out what test 4 is going to detail. It is a tough test in that there's lots of writing, right? So you don't have time to be thinking. You've got to just power through it. There should be shards of pencil flying and your paper ripping, and right? And you should just be writing constantly for this test. 7 questions in an hour and 25 minutes, right? So you've got to be ready. You've got to have your formula sheet ready. You've got to make sure that you have all your directions on there. I just gave a quiz in my other class for chapter 4, and I said, give me a second derivative test for arctan. And they said, I forgot how to do the derivative of arctan. I'm like, well, why isn't it on your formula sheet, right? You gotta have all of those derivatives memorized for Calc 2. So you might as well have them memorized now, but in case there's a chance for the brain just to go, what? You put them on your formula sheet, right? Every single derivative, including the ln's, right? I didn't put a real chain rule derivative of ln on chapter 3, but I could put one on chapter 4. Okay, so what is our arbitrary point here on this curve? What is our arbitrary point that we need here? Right? Why is nothing working today? There it is. It's x comma y, right? But I'm going to substitute the y with 4 minus x squared, right? So it's really, all right, x comma 4 minus x squared. And we're using our distance formula for our minimizing function, right? So y2, 4 minus x squared, minus 2 quantity squared, plus x2 minus x1 quantity squared, x minus 0 quantity squared. Everybody with me?
So far, so good.
Okay, good. Chris, yes?
Yeah, I'm with you.
Nice. So this one is nice to simplify. It's a good idea to simplify this. I can't seem to find my class here. It doesn't have to be done, but it's just going to clean it up a little bit. So I think I get, what, 2 minus x squared, quantity squared, plus x squared. I'm trying to do baby steps, trying not to do too much at once. 4 minus 4x squared plus x to the 4th plus x squared. And then I can rearrange it as more traditional highest power first. So minus 3x squared plus 4. So there's my distance. Again, noting the point that this distance can't be 0 and this distance cannot be maximized, right? We're going to get some weird criticals out of this. And of course, graphing this particular function would explain those weird criticals, and then doing a first derivative test might explain these criticals. But I'm not going to go there. I'm just going to find that critical value that gives me a point in the first quadrant. All right, derivative. We're writing our derivative now. You should already have it written down if you haven't done it already. Otherwise, start writing it now. You're not copying me. You're doing the derivative yourself.
That one should be pretty simple.
Yep.
Oh, the derivative of your...
The piece I want to minimize is the distance. Yeah.
Not of the original function, the distance.
No. Well, why would I get the derivative of the original function for that tangent line piece I did Wednesday? Right?
Okay.
So I like to notice that I can see my original distance function in here, and I think it makes it a lot easier just to put that in as d, right? So I'm going to say d prime of x is 2x cubed minus 3x over d of x. Right? I canceled the 2, right? And I noticed that that square root is my original function. So I like to put it in as an abstract function because I don't have to deal. It gets pretty messy when I do my second derivative, right? And why would I do my second derivative? To make sure my point that I get gives me a min distance, right? So second derivative should be positive so that I see I have a minimum, right? Well, critical values, I don't need any from the downstairs because the distance can't be 0. But from the upstairs, right, d prime of x equals 0. How am I doing here? Am I going too fast? Are we okay? Everybody's okay? From the upstairs, I get 2x cubed minus 3x equals 0. Or x times 2x squared minus 3 equals 0. So I get x equals 0. That's the one I think is kind of strange.
The ones in the numerator are like vertical ones or
horizontal ones.
Horizontal ones, and
yeah.
The ones in the denominator are like vertical ones.
Yeah. So I also get 2x squared minus 3 equals 0, which gives me x equals plus or minus square root of 3/2. And of course, I want the positive square root of 3, square root of 3/2, because that one's it's the one in the first quadrant, right? So the critical I want is x equals square root of 3/2. And of course, I could rationalize it, right? If I did rationalize this, what would I get? Rad 6 over 2, right? Either one for me is fine. Once we start getting into Calc 2, we don't care about rationalizing anymore. We did a lot of that in pre-cal. Always had your answer rationalized, right? Yes, Afsun?
So how did you know to pick only the positive?
That was my problem. I said, find a point in the first quadrant.
Oh, okay.
Yeah. And you'll see there's one in your homework where you have to find the 2 points. The 2 points that are min distance away from God, what is it called? What's the path of the Earth again? Not a circle, but ellipse. Oh boy.
Yeah. Like great circle or
an ellipse.
Okay.
Yeah. Right. The sun is bigger than us, the Earth, right? And so it acts like a magnet and pulls us, right? But you remember when you put two magnets together, they want to push each other away. So that's kind of what's happening with Earth. That Earth's getting pulled toward the piece with the larger gravitational field, and it repels, and then it slingshots back around the Earth and gets thrown way away, and then gets pulled back by the magnetic force again. It's pretty cool stuff.
Talking about the orbit, yeah.
Yeah. So once I found my critical value, I have to find two other things, right? Actually, three at minimum. I have to find the y point, the distance and that it is a minimum. Right, the value at the second derivative. So let's find the y point first. So y is 4 minus x squared, right? That's the original problem. So I get 4 minus 3 halves, or 8 halves minus 3 halves, or 5 halves. So there's my y coordinate. And it's always nice to make sure I've got this correct. Gosh, I can't.
Sounds like you're struggling, teacher.
I was up very late last night. I went to the baseball game, and it ended almost midnight.
Nationals?
Yeah.
Nice, nice.
So Desmos y equals 4 minus x squared, and I have the point square root of 3 halves, comma, 5 halves. Yeah, nice. And of course I have the point 0, 2. Nice. And you can see the perpendicularity there, right? Okay.
Yeah, it would be the perpendicular to the tangent.
That's right. So, let's find our distance. So distance at square root of 3 halves, right? And I had what? X to the 4th minus 3x squared plus 4, I think, at least. Let me look. Yeah. And I'm putting in my square root of 3 halves there, which is nice because I've got a 4th power and a 2nd power. So it's going to give me 9/4 minus 3 times 3 halves plus 4. Nice 3 there.
This is another one of those really tall problems.
So changing everything to a denominator of 4, I get 9/4 minus 18/4 plus 16/4. And it looks like I'll get square root of 7/4, or rad 7 over 2. And there's my min distance. So once I found my critical value, I probably shouldn't do this until I double check myself, but I did graph it, right? So I found the critical value, I found the y coordinate, I found the min distance. The only thing that's left for me to do is verify that it's the min distance, right? And so the way I do that is second derivative, right? So if we remember that d prime of x was 2x cubed minus 3x over d of x, I'm going to use a quotient rule to find my second derivative, right? So you're not copying me, you're erasing me. And the derivative of d is d prime. Sorry, yeah. So I get my d double prime from that loop. Make sure you tell me if you see a mistake. I think I'm okay. So I get d of x times 6x squared minus 3 minus d prime of x times 2x cubed minus 3x all over d squared of x. Can I leave the original function d in there? Yes, it's just going to get messy. It gets messy, that's all. But you're going to notice something when I plug in square root of 3/2, right? Because that's what I have to do. D double prime of the square root of 3/2 is D of 3/2, square root of 3/2. Okay, I know that already. Times 6 times 3/2 minus 3 minus D prime of square root of 3/2. And I know that already, right? In fact, what is D prime of square root of 3/2? What is this piece here?
Let's see.
It should be a 1 second thought. It's 0 because it's the critical value of the first
Because we already found it, yeah.
Yeah. So I don't even care about the rest of this. That piece is 0. So now I'm dividing by D squared of square root of 3/2, right? So look at what happens. D double prime of the square root of 3/2, one of those cancel, right? So it looks like I get, upstairs I get what, 9 minus 3, and downstairs I get the distance, square root of 7/2. And all I care about is that that is positive, and it is. Yes, up soon.
Should they? Oh, wait, I just saw it. Never mind. Thank you.
So I'm ready for my conclusion, right? What am I going to mention? I'm going to mention the point, the 2 points. I'm going to mention the min distance.
Is there a way to bring out the square root to the outside?
No.
Okay.
You're thinking of a log function.
Yeah, because I was just thinking, you could like square root or unsquare root the 12, and then put the square root on the outside of.
You're talking about this answer? You can rationalize it.
Yeah.
You get 12 right 7/7, but still positive. Still positive.
No, like still leaving the whole thing as a square root, like unrationalizing it. Cause,
no. Well, yeah,
okay.
You could square both sides, but don't do that.
Okay.
Yeah. You see, I've taken care of that square root by just calling it D. I don't even see a square root in my problem, right? I don't see that original piece in my problem because I don't see the square root anymore in D prime. And like I said, you could leave it in there, but it's messy.
Yeah.
So conclusion. The point square root of 3/2, comma, square root of 7/2. Oops, is that right? No, 5/2, right? Gives a min distance to 0, 2 on the curve y equals 4. Oh, the min distance of square root of 7/2 to the point 0, 2 on the curve y equals 4 minus x squared. That's not the best English, but you get the idea. In English class, that my teacher asked me for 2 pronouns, and I said, "Who, me?"
Rough crowd.
Yeah, sorry, I'm used to it. I've been teaching for 20-some years, so I'm used to the booze, to the jokes.
I like it,
All right, here we go. Chapter 5, ready to go. Anybody need a moment before I start chapter 5 here?
Professor, I have a question.
Sure.
Chimaka, why did you pick
square root 3/2 and not 0?
Well, because that was remember, I found a critical value in the first quadrant right there. So that's the point on the curve. And then I found the y-coordinate for it using the curve. And so so that's the point there, right? Looking at that, right? So you can see I graphed in blue that original critical value and the value in the y on the curve. Yep.
Okay.
Nice. Good.
Also, for the second derivative.
Yes.
If it was negative, does that mean the distance was wrong?
Yes, that's a good point. We know the distance can't be maximized. So if I did get a negative out of it, I'm showing that it's a maximum, but we know that can't happen. So that's a nice thing, right? By looking at the graph, we're going to know if we're right or not, right? And yeah, good question. And everybody noticed that I am not doing any of my graphing of my function and its derivative here, but you still could, right? You still could graph this derivative and make sure things are making sense, right? All right, here we go. Chapter 5. Yes, you're welcome. Yes, Officer, question.
Is the reason we can't maximize the distance because it's like an infinite function?
Yeah, exactly. So if you just kind of look at that curve, right? If you're just looking at that curve, you can imagine I could get a distance all the way down to here or all the way down to here, and it will keep going forever. Yeah. Yeah, okay. So no max there.
How did we decide our distance at the start? Did you just base it off of the function?
Yeah, well, this is one of the reasons why I like math. I get to play God. I get to create the question, right? I have this power. I can create the question, and you just got to answer it, right? So, yeah. So yes, just from whatever I tell you to do, that's what you're doing. Nice. Here we go. Chapter 5. Well, I can do. Yeah, that's good. Let's do chapter 5. I've got next week to tell you what's on the test, but you already know. A absolute min-max problem, a first derivative test for increasing, decreasing, a first derivative test for local min and max, a second derivative test for concavity, a second derivative test for inflection points, a geometric optimization problem, a min distance problem. There's my 7. Right there. That's it. That's your next test. And you will have to write like a mad person. People will come into the class. If we were in a classroom, they would come into the class that Friday and hear all the papers and the pencils marks and think everyone's insane because you're going to be writing so fast and so much, right? You should have 7 pencils lined up on the desk, all sharpened. All right, chapter 5, we're talking about integration. And we know what integration is, but it's so much more than what we had thought of before. It's finding the antiderivative, right? So antiderivative is like I'd give you y prime, right? 1 over 2 square roots of x, and then you would tell me y, square root of x plus c, right? So I give you y prime, you tell me the antiderivative, and we always have to have that constant of integration, it's called. But now what this thing is going to turn into is I'm going to give you the integral of 1 over 2 square roots of x dx. So you can see here now my operator is strange. My operator is behaving in 2 pieces. The argument is 1 over 2 square roots of x, but the operator says integrate with respect to x. So weird. The operator's like bookends, right? Like if I had said something like weird, like square root of 4, right? So you can see my square root piece I've written as bookends. So my operator's in 2 pieces here. Kind of weird. But guess what the answer is? The same answer as when I did my antiderivative, square root of x plus c. So in general, I guess you could say that the integral of f prime of x dx is f of x plus c, right? So you can really see that antiderivative piece happening in there. But there's a reason why we moved to this integration notation, okay? So what we're talking about in chapter 5 is methods of integration. So we already did some, right? All right, if I have a 0, right? I know I took a derivative of a constant. If I have a 5, I know I took a derivative of an mx plus b. If I have a power rule, right? If I have a sine or a cosine, right? We did a bunch of these. Am I right? Yes. Yeah.
Well, if you took the antiderivative of 0, you get just a number.
Yeah, exactly. The integral of 0 dx is c.
Just a constant. Could be anything.
Yep. So in chapter 5, we're going to do something called the area problem. We're going to do something called definite integrals.
And that one was just like the antiderivative.
Yep.
Right?
Yep. We're doing Riemann sums.
Yep.
We're going to talk about the fundamental theorem of calculus all today. We're doing all of these today. And then we have the rest of the semester to do integration methods. So meaning, how do you integrate when you have a chain rule involved? And we will finish those integration methods in Calc 2, at the start of Calc 2. We'll have about 12 to 15 different methods. Like we had a product rule, a quotient rule, implicit chain rule, right? We had all those different things happening in derivatives. We have equivalence happening with antiderivatives, with integrals. So that's our overview. Let's start with the area problem. Okay? Everybody okay here?
I had a professor that taught fundamental theorem of calculus in like week 2. So I remember that.
Yeah, that's not
terminology.
It's not a difficult thing. It's simply saying that if you take a derivative, you get slopes. If you undo the derivative, you get area. And so
yeah,
that part is weird, and it's a God moment. Like, what? How can you even explain it to somebody, right? As soon as you start to try and explain what God is, we're wrong, in my opinion. But it's something so, I don't know, so something special, something connects deep to the universe that we probably don't quite understand yet.
The proof for it is very beautiful. That's what I remember.
Yes. And so what's true about derivatives and integrals is they are inverse operators. So that's the fundamental theorem of calculus. Integrals undo derivatives, derivatives undo integrals, and one gives a slope and one gives an area. That's basically the fundamental theorem of calculus as in a quick elevator pitch. So let's talk about our area problem. Now we need some things from pre-cal, okay? We need some things from pre-cal. So I need a couple of series And these should go on your formula sheet for the Chapter 5 test and for the final. Okay. So the series I need to remember is that the sum from I equals 1 to n of a constant is n times the constant, right? If I add up 5 n times, I get 5n, right? If I add up the indices, so 1 plus 2 plus 3 plus 4 plus all the way to n, I get n times n plus 1 all over 2. If you had pre-cal with me, we did these. I guess I should write out the first one too, right? It's c plus c plus c plus dot 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 plus c n times, right? The next one is if I take the indices, and indices meaning the first number, the second number, the third number, the counters, right? An index is simply a counter. So if I take the indices squared, I get 1 squared plus 2 squared plus 3 squared plus dot 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 all the way up to n squared. And on that one I get n times n plus 1 times 2n plus 1 all over 6. I proved these in my pre-cal class. Anybody else recognize them at all? Yeah, nice.
Oh yeah, I love these.
And the last one that I'll have you deal with is the indices cubed. So that's 1 cubed plus 2 cubed plus 3 cubed plus dot 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 plus n cubed. Go ahead.
This is the one where you learn about exclamation point.
Yeah, factorial.
Yep.
Yes, so these are the series I want to use, and if you don't recognize it, I'm giving you up to a cubic polynomial here, right? Like x cubed or plus x squared plus x plus 1, something like that. Because those are easy to integrate, right? Polynomials are easy to integrate. It's just a bunch of power rules, basically. Does anybody want any of these proved or demonstrated?
Proof like how?
How would I prove it? I prove it by induction. If it's any of these two, the proofs are very simple. But does anybody want any of these proved or demonstrated?
Yeah, can you demonstrate the last two? Just the last
Sure. How about just star here? Let's just do one, because if I do one, it's the same as doing any other one. Let's do the sum from I equals 1 to 7 of I squared, right? So 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. So I get 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49. So I get 50 plus 40 plus 25 plus 25. 50 plus 40 plus 25 plus 25. So 140. So that was my left-hand side of the equation. Now the right-hand side of the equation is going to come from n times n plus 1 times 2n plus 1 all over 6, where n is 7, right? So I want to look at 7 times 7 plus 1 times 2 times 7 plus 1 all over 6. So I get 7 times 8 times 15 over 6. Help me. 7 times 2 times 4 times 3 times 5 over 6. So the 2 and the 3 and the 6 go away. And I've got 28 times 5. I'm going to just guess. Oh yeah, it's 140. Right, so you get the idea. So you could look at any of these up to any number and verify them. Jesse, comment?
I liked these sums so much that when we were doing in pre-calc the what form is it? What the leading number for binomial?
Yeah. The binomial coefficients, yeah.
Yeah, and the triangle.
Pascal's triangle. Yeah.
Pascal's triangle. I liked that so much that I figured out. I was dumb braining in the calculator until I figured out a correct summation representation of the actual leading, and that was before the teacher showed us
That's cool.
the formula for it, and if I remember correctly, it wasn't done as a sum; it was done differently.
Yes. And it's got a N choose C in it. Yeah. Okay. So back to this area problem. Let's, for example, take a look at the integral of, let's say, 3x plus 1 from 2 to 5 dx. So I want to draw a picture of this. Now notice I have some bounds here. I have a lower bound and an upper bound all of a sudden. So this is called a definite integral, and this one's going to give me an area. If I just did this integral, 3x plus 1 all to dx, right, with respect to x, there I'm just saying give me the antiderivative. So on the top problem I'm saying give me the area. On the bottom problem I'm saying give me the antiderivative. Okay? So what is our antiderivative here? What is our antiderivative?
Maybe it's like a 1.5.
Yeah, it's 3x squared.
3x
squared over 2. Remember, add 1 to the exponent and divide by the new exponent, plus x plus c.
Yeah, I just wasn't thinking about it in terms of fraction. I was thinking about it. It was going to be half. I just gave it as a decimal.
Is everybody okay here? So I had a 3x squared. A 3x. I added 1 to the exponent divided by the new exponent. I had a derivative of 1, so I must have had a function of x, because when I took the derivative of x, I got 1 plus c plus my constant of integration. This one up here is going to become the same answer, 3x squared over 2 plus x, but I'm going to evaluate at 5 and then 2. So meaning I'm going to put 5 in, put 2 in, and then subtract them. And so you can kind of get an idea of why the c is not there anymore, because I'm going to eventually do c minus c. It's going to go away. So I've got here 3 times 5 squared over 2 plus 5 minus 3 times 2 squared over 2 plus 2. So this is my process for a definite integral to find the area under the curve. So it looks like I have 75 over 2 plus 5 minus 12 over 2 minus 2. Double check me there. 25, 3 times s plus 5, yes. And then 4, 12, yes. So 75 over 2 plus 5 minus 6 minus 2. So I have 75 over 2 minus
That should be
3.
correct, yeah.
Yeah. And that is 75 over 2 minus 6 over 2. Morning. It is 69 over 2. And there's my area under my curve. I want to show you real quick how to verify this on your calculators. So 34.5 is what my calculator should give me. So on my calculator here, well, it's nice to do it on Desmos too. So let me do it on Desmos real quick. Integral from 2 to 5. I just start typing integral, and it gives me an integral symbol. Of, what was it, 3x plus 1? dx.
Yeah.
And there it is, 34.5. If I make it y equals, I think I get a nice picture. Do I? No. So, but on our calculators, so that we definitely get this one right on our test, on our Chapter 5 test and on our final, I go into y equal and I put in my function, 3x. Oops. Some days my mouse just doesn't work. 3x plus 1. I want to make sure I zoom standard and make sure I can see the graph. I need to be able to see the graph and from 2 to 5. I need to be able to see it from 2 to 5. I think this is fine. I need to be able to see the x scale from 2 to 5. Let's find out though. I go second calculate integral from number 7, and I start at 2, and I go to, come on, and then I go to 5. Oops. And enter again, and then it gives me my area, 34.5. I'll do another one very soon. Okay.
Is under calc?
Yeah. So second calculate 7 for integral, and then hit my lower limit 2, enter, upper limit 5, enter, and it gives me the area, shaded area under the curve. So looking at that picture, right, the integral from 2 to 5 of 3x plus 1 with respect to x, this is the area under the curve. By the way, under what curve?
The curve of 3x plus 1?
Yes, the derivative curve of the the derivatives curve. So here's my 3x plus 1 from 2 to 5, and you can see that I'm getting an area here underneath my curve that's split into two pieces, right? So I got an area of a rectangle, and I've got the area of a triangle. So this is going to be equal to the area of the rectangle plus the area of the triangle. And of course, I can figure out that area without doing any calculus, right? How wide is my base? I have a base of 3, right? I need to figure out the coordinates of my point. So when I plug in 2, right, what do I get for my height here? I get 7. And my height, when I plug in 5, what do I get? 16. So how tall is my rectangle is 7. How tall is my triangle? 9. Right, because the total height's 16. Yes, everybody with me here?
Yeah, so far so good.
Yes.
Good. So I get my area is 3 by 7 for the rectangle, plus 1/2 the base times the height, so 1/2 of 3 by 9, right? So that's 21 plus 27 over 2. Did I do that right? 3 times 7 is 21, not 27. Right? 3 times 9 is 27. Yes, 27 over 2. So that's 42 over 2 plus 27 over 2. There it is, 69 over 2. Same answer.
Nice.
So kind of weird, right? Kind of weird that the area under the curve, the area under the derivative curve is given to me by integrating, right? And then weird, the slope of the curve of the derivative, right? So when I take a derivative, I get the slope of a curve. When I have the function that tells me the slope of the curve and I integrate, I get the area under that curve. This is fundamental theorem of calculus. This is like, what the hell's really happening here, right?
This is when you go to the number file YouTube and scratch your head at what those old men 200 years ago were thinking of.
Yes. Well, those old people in ancient Egypt, ancient China, ancient India, ancient Greece, that's who started all of this stuff. People from the Middle East, people from Africa, people from Asia.
Absolutely.
Yeah. So we want to do one more thing with this today. How are we doing on time? We're good. So I'm looking at this integral from 2 to 5 of 3x plus 1.
Oh, I think you didn't number what the last page was. That was still 5.1, right?
Yeah, I'm just doing the area problem today. But I'm actually doing 5.1, 5.2, 5.3, and 5.4 all at the same time.
It's all together.
All together. So
book is too slow, etc., etc.
Yeah. So I want to show you that this is equal to the limit as n goes to infinity of the sum of I equal 1 to n of f of x sub i's times delta x's. And it turns out that these guys are rectangles. So this is the width of my rectangle, and this is the height of my rectangle. So if I draw that picture again, from 2 to 5, and I always use right-hand rectangles. So for example, I'm going to cut this thing into 4 pieces. And you can see I'm getting the height of my rectangle from the right edge, from the right corner. So this particular height is f of 5, right? And this particular width is delta x. So I'm going to get the area using these rectangles. Now, is this an overestimate of the area or an underestimate of the area?
Definitely over.
Yeah, over. You can see the pieces on top of the curve, right? I want the area under the curve, and I've got a little bit of extra area on top of the curve. But notice what happens as n goes to infinity, right? Look at if I did this many rectangles. Look at my overestimate now. It's a lot smaller, right? You can see all my rectangles now. So as I go to an infinite number of rectangles, I'm going to get closer and closer to the actual area under the curve. So this, I'm calling this right hand, or right side, I can spell it, right side rectangles, right side rectangle Riemann sums. So I'm going to give you this formula, but of course you can put it on your formula sheet. Delta x is always going to be b minus a over n. For us, delta x equals 5 minus 2 over n. So I'm going to take that base and cut it into equal pieces, and that's my delta x. So for us, 3 over n. My x sub I is going to start at the beginning. It's always going to be a plus delta x times I. So for us, x sub I is 2 plus 3i over n. So I'm saying, oh, start at 2, but then move to the next delta x. Okay, then start there, move to the next delta x, and then to the next delta x, right? So I'm going to keep adding a delta x as I move to the right for each rectangle.
We always start with x and end with y. Kinda.
Where's the y?
Well, I'm just thinking about y as the answer, I guess.
Yeah,
It's usually
sure. Yeah, that's fine. Yep. Now I want to find f of x sub I, because I need the width of my rectangle right here, and I need the height of my rectangle, right? So this is going to be 3 times x plus 1, and in there I'm putting my x sub I. So it looks like I get 6 plus 9i over n plus 1. So 7 plus 9i over n. And this is my height of my rectangle. I didn't need those last parens. Anybody feeling a little overwhelmed right now, or?
This is recorded, right?
Yes. If you're not feeling overwhelmed, then you didn't have my experience. I was very overwhelmed when I first saw this stuff. So just be patient. We're going to do it every day. You'll get used to it. It'll become easier, right? I'm kind of just doing it. I'm not even explaining anything. I'm just jumping in the pool, right? So
the water's cold.
yes. So you see here, and I already know it, 69 over 2 was my area, right? But I'm looking at the limit as n goes to infinity of the sum of the areas, okay? So, and the way I'm getting the areas is I'm looking at the first rectangle and the second rectangle and the third rectangle, and I got what? 7 plus 9i over n for my height times 3 over n for my base, right? Remember, I'm doing the sum of all the rectangles there, right?
When we're talking about history of calculus, isn't this one of like the first problems that what was it? Not Newton started with the whole concept of infinitesimal calculus.
Yep.
I forget who that was that pioneered that.
Newton.
Okay, I was right.
Yeah. So, by the way, just real quick here before I go further, as I do this limit, as n goes to infinity, right, of the sum, by the way, that's the Greek letter sigma, right? So it's the Greek letter S, right? F of x sub I dx, delta x. What does the limit do to my sum? It becomes the letter S, the integral. And delta x becomes dx. Infinitely small widths of the rectangles. And of course my function is still f of x. Right? So that's kind of a beautiful little piece of this, is that this letter S becomes the integral, which is a letter S. And the delta x, right, becomes dx. So
yeah, it's useful
yes,
reusing the letters and So that's why math hits us up with the Greek alphabet so much.
Yeah. So limit as n goes to infinity of the sum of I equals 1 to n. And now I'm distributing here. I got 21 over n plus 27I over n squared. And you can see my 21 and my 27 from the earlier calculation when I was doing the area of the triangle and area of the rectangle. Now, I want to split this into two sums. So I'm doing the limit as n goes to infinity of two sums. The sum of 21 over n plus the sum of 27I over n squared. And I want you to notice that my sum is dependent upon I. I is the piece that's changing. I is 1 and then 2. The index, remember they're indexed. The first rectangle, the second rectangle, the third rectangle, the fourth rectangle. All the way up to the last rectangle, which is n. So it's some fixed number. So meaning I can take that piece outside of my rectangle, of my sum. So I've got a 1 over n times the sum of 21 plus 27 over n squared times the sum of I. That's a 21. But I have a series for the sum of 21, right? If I add up 21 n times, yes? If I add up 21 n times, I get 21n. And if I add up I n times, if I add up my indices n times, I get n times n plus 1 all over 2. So from my series that I have in pre-cal and memorized or written on my formula sheet, I know the sum of a constant. I know the sum of the indices. So I get the limit as n goes to infinity of, looks like 21 plus 27 over 2 times n plus 1 over n. Right, when the n's cancel there, right? And I want to just distribute that piece. So I get the limit as n goes to infinity of 21 plus 27 over 2 times n over n plus 27 over 2 times 1 over n. So I'm just distributing here. So it looks like I get the limit as n goes to infinity of 69 over 2 plus 27 over 2n. And remember, it was an overestimate. I got too much area, right? But now I'm ready to take my limit. And what happens to 27 over 2n when I let n go to infinity? Where does that piece go?
It goes to 0?
Yep. There it is. There's my area.
That's that bit where we get to cheat and divide by 0.
Yeah.
But not by doing it directly.
Yeah, it's a limit, right? We know where it's going. Any number over an infinite number is going to go to 0.
Oh, right. We're not putting in 0. We're
Putting in
getting
a
0.
billion. Yeah. Take $1 and split it among 100 people. Everyone gets a penny. Take $1 and split it among 1 billion people, and no one gets anything. Right? It's just this limit that we did in chapter 2, right? When I have infinite limits and the denominator dominates, right? We know the limit goes to 0. Pretty cool, isn't it?
really, it's better to think about this whole stuff in the context of all the stuff we had at the beginning of class.
Exactly. Pretty cool.
Because it all
Yeah, it's crazy how it all connects.
comes together.
And if you remember, I said that about calculus. Unlike pre-calculus, it was scattered. It was all over the place. And you see, this thing is just coming to this beautiful summary of everything we've been doing, right? And to with respect to your fields, everybody, biochemistry, engineering, computer science, these integrals are going to give us results. So, for example, an integral could give us a force. An integral could give us an amount of a medicine that should be administered. The integral solutions give us answers to real life things. Okay, so just like we learn multiplication and it looks like a rectangle, we're learning that these integrals are, right, adding up rectangles. So, but they have deeper meaning when we go further in our fields. So one of the pieces that we did in our class, Calc 1, was applications of derivatives. One of the things we're going to do in Calc 2 are applications of antiderivatives, applications of integrals, okay? And it's physics stuff, it's engineering stuff, it's bio, it's chem, it's all of these things, right? So you make sure in your Calc 2 book, which is our same book, by the way, you look at the chapter dedicated to your field of study, okay? So if you're a biologist, look at the natural science, look at the applications of integrals in the natural sciences. If you're an engineer or a physicist, look at the physics applications, right, in Calc 2, okay? If you're a computer scientist, you just want this version of everything. You want this mathematical version of it. You might work for a medical company. You might work for an engineering firm, right, as a computer scientist. So, but you need to understand the math. And of course, the math majors, when you take advanced calculus, okay, Noel, when you take advanced calculus, so Calc 300 and Calc 400, right? We're taking Math 181. We're taking Calc 1. You'll take a Math 300, which is Advanced Calc 1, and then a Math in the 400s, which is an Advanced Calc 2, and you'll be proving everything in calculus. So, what do you think? Pretty interesting stuff here, isn't it? This integration. Nahome's like, oh my god, I don't know what the hell's going on.
I remembered to ask about the groups for the group project.
Oh,
right?
yes. Is anyone looking? Right, we're asking. Is anyone looking for a group to join?
Yes.
Nahome, nice. Anybody willing to? Nahome, what's your major?
Computer science.
Beautiful. Anyone else with a computer science major that is willing or open to working with Nahome on the project? Or a math major. Noel, if you want to work with.
Yeah, I can do that.
Nice. That's good. It's a good combination, math major, computer science major. But you're taking, well, Noel's taking more math, but he's taking the same math that you're going to be taking home. So that's good. Good to make a connection with someone into class.
I wanted to be a math major, so but yeah, I just picked computer science. But, yeah.
Yeah, no, I think it's perfect because math majors will take computer science classes. They have to. If you go to University of Maryland, you have to anyway.
The Python is how you get the answers for
Yeah,
for
Python.
the math stuff.
Yeah, I'm teaching discrete structures in computer science right now, and we use Python in the class. So, all right. We'll do another problem Monday. We'll look a little further into fundamental theorem of calculus, but basically we did 5.1 to 5.4 today. But I'll do some more Monday. Let me stop my recording. You've got some homework to